So we have 1D, one-dimensional heat equation. Now assume that we have a rod, this one, of length L. So I put 0 here and L is here. A finite rod of length L. And assume that this is a heated rod. So initially we have the temperatures, say f of x, and I will denote u xt be the function that describes the temperature of the rod at the position x between 0 and L. So for example here, x between 0 and L, and at the time t bigger than or equal to 0. So this u x comma t is a function with two variables, x and t. And we will try to solve for this u x t with the heat equation given by u t equal to k times u double x. Here ut, you can also see that they write du over dt. So partial derivative of u with respect to t equal to k times du over dx squared, d squared, d2u over dx squared. The partial derivative with respect to x, and you do it second order partial derivative. I use this notation to make it simple. K here is a constant, and it is a thermal diffusivity. Thermal diffusivity. So depend on the material of the rod. For example, material and K with unit centimeter square per second. For example, if we have silver, then K equal to 1.7. If we have, say, iron, the rod is made of iron, then we have K is 0.15. So we first have the heat equation, and we will have a few conditions. The first one is the endpoint condition. We have two endpoints correspond to 0 and L, the two ends of the rod, here and here. So in this case, we consider the Dirichlet condition. The temperatures U at the N0 T equal to U at L T are both 0. So we keep the two ends of the rod in ice. So we always have temperature 0 degrees Celsius in the two ends. And we do 1D heat equation. So if, let's say, the two ends here are 0, if the heat want to escape, it will escape through the end. And we do not allow the heat escape in the other direction. We only consider 1D heat equation, one-dimensional heat equation. In this case, two ends always have temperature 0. And the last condition will be the initial condition. So this condition says that at the time t equal to 0, u x comma t is f of x. So t equal to 0, u x 0 equal to f of x. So at time 0, we have a heated rod with some profile, the temperature profile f of x can be something. For example, I can choose that I heat this rod so that at the beginning we're working with ux, 0 equal to 100 degrees Celsius, for example, or can be any function in x. We try to solve for this uxt. So the question we have is this one. We have a heat equation, we have the endpoint condition, and we have the initial condition. The methods we use here is separation of variable. We have two variables, x and t, u, x, t. And this method says that we can separate that u, x, t equal to x, a function in x, multiplied with a function in t. As soon as we have this, and we will use this one to solve uxt. And we can do it easily by just plug in this heat equation. To apply that is easy, but to show that this method will give us on the solution is harder. We will just derive the solution using this separation of variable. So here, how do we do it? We need to compute the partial derivative with respect to t and to x. U t equal to x times t prime, because when you do derivative with respect to t, these terms or these factors is just a constant with respect to the time. So x times t prime. Similarly, u double x is x double prime times t. Plug in the heat equation ut x t prime equal to k times u x k times x double prime t. Now we want to separate that. One side you have t, one side you have x. And to do so, I will divide both sides by k times x times t. Or in other words, I multiply 1 over k times x times t to both sides. 1 over k x t, k x double prime t. See that on the left, x and x cancel out. On the right, k and k, t and t. That gives us t prime over kt equal to x double prime equal to over x, and I let it be minus lambda, and we choose it to be minus lambda to make the equation nicer when I write down like this. This one, for example, x double prime plus lambda x is 0. So it's always for this plus lambda x. The other ODE we have is t prime plus lambda k t 0. We will try to solve these two ODE, the first one and the second one. And let's solve the first one first. I will need to use the two endpoints condition I have here. We have u0t equal to ult 0. So we use this right now. u0t equal to x at 0 times t at t. This one equal to 0. We don't want t of t 0 for all t. This one is true for all t bigger than equal to 0. And therefore x at 0 must be 0. Similarly, we use u l, t. X at l times t at t is 0. And this one equal to 0 for all t bigger than or equal to 0. We don't want this one is 0. So x at l must be 0. Now the first ODE here with the two conditions, x double prime plus lambda x 0, x at 0 equal to x at L 0. So we consider three cases for lambda. Case 1, lambda negative. Case 2, lambda 0. Case 3, lambda is positive. So for the first case, lambda negative, I can suppose lambda write as minus alpha square negative. So alpha, choose it to be non-zero. I choose it to be positive. Square of this positive minus that negative. The equation x double prime minus alpha square x equal to 0. And now you let x be e power, let's go r times x. So x prime will be r e power u prime e r x double prime r square e r x, and replace that here into the equation. You have r square e r x minus alpha square e r times x equal to 0. E r times x in common, you can put it out and you can divide both sides by that because this is always non-zero. Divided by e power rx, you have r square minus alpha square 0. So r square equal to alpha square, or r equal to plus minus alpha. And with that, we have the general solution. X of x equal to exponential alpha x, let's say c1 plus c2 e minus alpha x. So this is our solution. We can also write as, say, a constant a times cos alpha x plus b sin alpha x, because we call that cos say alpha x is exponential alpha x plus e minus alpha x divided by 2, and sin alpha x is e alpha x minus e minus alpha x over 2. So you can either write this one or this one. Now, because of our condition x at 0 equal to x at L equal to 0, we have x at 0. Let's say I want to choose this one. X at 0 is a times cos 0 plus b times sin 0. A cos 0, b hyperbolic size 0. This one is 0. Cos 0. Cos 0 is 1 plus 1 over 2. A. Sin 0. Exponential 0. So 1 minus 1, which is 0. B times 0, which is a. This means a must be 0. And now we use the second condition, x at L. X at L, a is already 0. So these terms disappear. We have x at L b sin alpha times L. B sin alpha times L. Alpha non-zero, L non-zero. This hyperbolic things non-zero. So x at L is 0, which gives us b must be 0. In this case, a and b are both 0, which means x of x is 0 for all x. for all x between 0 L. And we don't want that. We don't want trivial solution. So the first case, lambda negative, gives us the trivial solution. Now we consider case 2. Case 2, lambda 0. So we have the equation x double prime plus lambda x plus 0x equal to 0. X double prime equal to 0. X double prime is 0. X prime equal to, say, a constant a. X must be a times x plus another constant. This is x of x. Now we have two conditions. X at 0 equal to 0. X at L equal to 0. Use that now. X at 0, a times 0 plus b. So b must be 0. b is 0, so x of x is a times x. X at L is a times L. This one again 0. This gives us a is 0. So the second case also gives us b 0, a 0. Trivial solution again. X of x equal to 0 for all x between 0 L. We don't want trivial solution. Case 3. Lambda positive, and I write down lambda as alpha square. I choose alpha positive. And again we solve x double prime plus lambda x equal to 0 plus alpha square x equal to 0. And you do exactly the same methods as the first case, and you have exponential lambda, right? Similar as before. In this case, because alpha square, so r square plus alpha square give us imaginary. That's why we use Euler formula. You bring this one to the cos and sine. So this one similar as case 1. Similar to case 1. This one I will just do it quickly, and I say that similar to case 1, we have x of x equal to a cosine of alpha x plus b sine of alpha x. So the negative one gives us cos and sin. The positive one gives us cosine and sine. Now we use the two conditions, x at 0, x at L, 0. X at 0 equal to a times cosine 0, b sine 0. X at 0 is 0, cosine 0 is 1, and plus 0. So a equal to 0. This gives us x of x is b sine alpha x. Now we use x at L, b sine alpha L. But x at L is 0. And we do not want b also 0, because if b is 0, we again have the trivial solution. So sine of alpha L 0. So we have sine 0. Alpha L must be here or here. So alpha L must be a natural number L, n, because we choose alpha to be positive. Alpha L is positive. Alpha L is equal to n pi, n natural. And to make it precise, and write bigger than equal to 1, because our alpha positive. So I don't want n equal to 0. Natural number bigger than 0. So our alpha n pi over L. We have alpha lambda is alpha square, right, as we said. N square, pi square, L square. See, we have so many n. Therefore, I will just write lambda n for this particular n. For given n, we have one lambda n. This one is our eigenvalues. Eigenvalues lambda n for this problem. And you have eigenfunction x. Let's call xn of x. Xn of x, which is something b just a number, a scalar. I throw it away. I just keep this function because any scalar multiplication, any scalar multiple of this one will gives us another eigenfunction. Psi alpha x. Psi alpha is n pi over L. Psi alpha x. This is our eigenfunction. So this is a case we have non-trivial solution. Now we have lambda and we have x. We use this lambda to solve for t. Remember that at the beginning we have two ODE. We now solve for the second ODE. Now I plug in lambda n square pi square L square. T prime n square pi square over L square times k. I put k here. Multiply t 0. Remember that this one is just a number. So it is of the form t prime plus a mu t 0. And this one we know the solution t of t must be e power minus mu t. So we have in this case t of t equal to e minus mu is k n square pi square L square mu t. So mu in this case is just this whole thing here. Because it's involved n, so I just put tn for given n 1, 2, 3 and so on. We have xn, we have tn, we multiply them together. We have one building block un. Un xt is xn times tn. Xn is this psi n pi x over L times tn. Now by superposition principle we have by superposition principle we can just take the summation of all such un. The general solution uxt equal to summation cn un xt and run from 1 to infinity. So we have summation n from 1 to infinity, a constant cn, multiply the entire thing here. Now remember that we have the initial condition at the beginning we did not use. Now we use it. U x comma 0 is f of x. We will use this initial condition to solve for this coefficient cn. U x comma 0 equal to summation n from 1 to infinity cn psi of this. So because we plug in t equals 0, psi n pi x over L still there, exponential something times 0. So e power 0 is 1. Therefore u x comma 0 equal to this one. This one is f of x. You see that this formula is exactly the Fourier sine series of f. Fourier sine series of function f of x, and therefore Cn here, the coefficient Cn is given by 2 over L 0 L f of x sine n pi x divided by L dx. Now conclusion. The solution of the heat equation with the Dirichlet condition that we have at the beginning. This heat equation with Dirichlet condition here has a solution u xt equal to this summation, where Cn is given by Fourier sine series coefficient, where Cn equal to this. And this is how we derive the formula of the solution of this heat equation.